Section 6.2, work energy theorem and kinetic energy. So we're going to derive a pretty powerful equation. If you don't like derivations, you can skim over this. If you want more details on the derivation, the textbook has a bit more details as well. So we'll consider that there's some net external force acting on an object, similar to how our crate on the back of the truck had a net external force that was accelerating it forward. That happened to be friction, but here we're making it a little more general, just some net force, which we have written here with the red label. The object, displaced by a distance s, is displaced in the same direction as the net force. Well, if we wanted to calculate the work, it would just be the net force times the displacement, right? Because we'd have cosine of 0 degrees, that's just 1. And we know that the net force by Newton's second law is equal to ma. So the work is just equal to mass times acceleration times displacement. Cool. This is what we actually saw on the truck accelerating a crate. Same thing here. But we can derive a more useful result if we pay attention to the acceleration times the displacement. And we've actually seen a case where we had acceleration times displacement. But instead of working with s, that was back when we were working with x. So if you think of acceleration times displacement, we saw some kinematic equations that actually showed that. So let's take a closer look. So work is equal to mass times acceleration times displacement. If we remember that acceleration times displacement, we saw that with a times x. In the equation of kinematics, for the final speed or velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. This is the same thing, right? Instead of x, we are now using s, but it is an equivalent calculation. So if we rearrange this equation to solve for the acceleration times the displacement, we get the acceleration times the displacement is 1/2 final velocity squared minus initial velocity squared. And we can substitute that in for the a times the s. So then we have m times this 1/2. So if we pull the 1/2 out, distribute out the m and the 1/2, we're left with that work is equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. This is where we can take a moment to define this quantity, 1/2 the mass times the velocity squared, or more precisely, the speed squared. This is something that we call kinetic energy. The kinetic energy of an object with mass m, speed v, is given by this equation, 1/2 mv squared. This equation pops up all over physics, so it's a really good one to sink your teeth into. 1/2 mv squared. We're going to see it quite a bit. Note, it is the speed here, more precisely than velocity, because the direction doesn't matter. To convince yourself with that, if you plug in a negative velocity, because you're going in the negative direction, it would still come out to a positive kinetic energy because that term is squared. So we want to hang on to this idea of kinetic energy, which, by the way, any guesses what the units of our kinetic energy are going to be? Joules! So that's pretty cool. I'm a fan. All right, and this brings us to what's known as the work kinetic energy theorem, because this would then be our final kinetic energy minus our initial kinetic energy is equal to the work done. So let's take a look. So the work energy theorem says when a net external force does work on an object, the kinetic energy of the object changes by the amount of work done on it. So if you have work being done, that will change your kinetic energy. So your final kinetic energy minus your initial kinetic energy will give you the work. And that can be calculated in terms of the overall kinetic energies if you know them, or with our kinetic energy equation, 1/2 mv squared. So that's depicted up here in the example with the jet, that the jet has a force, net force acting on it, and that is in the direction of the displacement. So it has some initial velocity. As that net force continues to act on it with the thrust of the jet, its final velocity is greater than the initial velocity. That's because that net force did work over this displacement to change both the speed and thus also the amount of kinetic energy. Now, the sign here does matter, and this is where our positive and negative work comes into play. If the force does work that is positive, then that's going to say that it is increasing the overall kinetic energy. The jet is now going faster. If the thrust or some other force acting on the jet does negative work, maybe brakes, for instance, doing negative work, that's actually going to act against the motion of the jet to reduce its kinetic energy, so that the final kinetic energy is less than the initial kinetic energy, and you get a negative sign on either side of the equation. So that's a pretty nifty side note. All right, so now that we have this definition of work-energy theorem and kinetic energy in general, let's take a look at an example. So example 4, Deep Space 1. The mass of the space probe is 474 kilograms and its initial velocity is 275 meters per second. If the 56 millinewton force acts on the probe through a displacement of 2.42 times 10 to the 9 meters, what is its final speed? Right, so looking at this, just before we even start analyzing it for solving it, 56 millinewton force, that's what the little m in front of the n is standing for, milli, right? That's 10 to the minus 3. This is a tiny amount of force acting on it, because we can think of 1 newton is about the weight of an apple. So this is half of an apple. Half of an apple's weight is pushing the space probe that is 400, almost 500 kilograms. Wow. So it doesn't seem like it could do that much, but it is acting over a large displacement, 2.42 times 10 to the 9 meters. So we might see a significant change in the speed of it. Something we can investigate, all right? So we note that we're given the mass, we're given the initial velocity, which is going to be our v sub 0, and we're given the net force that acts on it, because it's the only force acting on it. That's the advantage of being in outer space. You're pretty isolated from other forces. And then finally, we have the displacement S. So this is a good amount of things that are provided here. What are we trying to solve for? Final speed, that's going to be our v sub f. So then we have to think, okay, what tools might help us out? Well, I have a feeling it's going to involve the work-energy theorem and kinetic energy. Just a hunch. So we take a look at our work-energy theorem. It says that the work is equal to the final kinetic energy minus the initial kinetic energy, which we can remember our kinetic energy is equal to 1/2 mass times the speed squared, 1/2 mv squared. So 1/2, the mass doesn't change, so we can just write m, but I'm going to do a v sub f for the final speed squared minus 1/2 mv initial squared. All right, and as we're looking at this, we can note that, hey, I know my mass, I know my initial velocity, I know my mass here. I want to find my final velocity. What about my work? Well, I don't know that yet, but maybe I know some other ways to calculate work. Hey, I think I do. In addition to the work being equal to the change in kinetic energy, we also know that our work is equal to the force times cosine of the angle theta times the displacement. And so checking through this, we know our displacement and we know our net force. What angle would we want to use here? Well, this is where our picture is really helpful, and they gave us a picture, which is very nice of them. The force is acting to the right, which is in the direction of the velocity, and the displacement is in that same direction. The problem would have had to state this if they did not include the picture, just as a side note. But the picture shows that they are all acting to the right, So if they're all acting to the right, that is the same direction. What is our angle theta then? Our angle theta will just be 0. So we usually have to figure out the angle ourselves given the description in the problem or in the picture that is included. All right, so cosine of 0 will be 0. That tells us in this case our work will just be the force times the displacement. So let's, with all this in mind, take a look at what the solutions show for this, see how they compare. Aha, we have our work energy theorem, right? That the work is equal to the change in kinetic energy, Ke final minus Ke initial. That matches what we just wrote on the previous slide. Great. Kinetic energies are plugged in. Work is with the net force times cosine theta times S. Cosine of theta is 0. We have the force, we have the displacement, we know the mass, we know the initial velocity. So at this point, we can algebraically solve for the final velocity. And if you're comfortable with it, you can just plug in numbers and move the number, combine numbers together to get the right answer. You can also work in terms of symbols and rearrange it to solve for V final. That can be a really good practice. To do that, I would probably first multiply by 2 over m, so that you have 2 divided by m times the work, so the net force times the displacement, since cosine of 0 is just 1, and that is equal to the final velocity squared minus the initial velocity squared. So then you add the initial velocity to the other side and take the square root. 2 over m times the net force times the displacement plus the initial velocity squared, the initial speed squared, is equal to the final speed. And the final speed, whichever way you calculate it, you should find that it is 805 with the units of meters per second, proper SI units here. 800 meters per second, can you imagine? That's more than 8 football fields in a second. Whew, that is zipping along. So this highlights the idea of how we can use the work kinetic energy theorem along with our understanding of kinetic energy in order to figure out how the velocity or the speed of an object is changing. Pretty nifty. One more example. We take a look. Let's see. So, oh, too far. Example 5, downhill skiing. A 58 kilogram skier is coasting down a 25-degree slope. She accelerates down the slope because of the gravitational force, even though a kinetic frictional force of a magnitude 71 newtons opposes her motion. Ignoring air resistance, determine the speed at a point that is displaced 57 meters downhill. All right, so first, what is this problem giving us and what are we trying to solve for? So we have 58 kilogram skier. What is that telling us about the skier? Well, the units give us a clue. Kilograms. Is that the weight or the mass? Kilograms are units of mass. So that's going to be our mass is 58 kilograms. We have the angle of 25 degrees for the slope. Acceleration because of the gravitational force. So we know that there's some gravitational force present, mg, and there's a kinetic frictional force, F sub k, and it gives us the magnitude of that frictional force. Great. And then it mentions this displacement 57 meters downhill, displaced 57 meters downhill. So that gives us a clue that this 57 meters is going to correspond to our displacement. Right, now what are we trying to find? We're trying to find speed. So it's going to be a v that we want to find. And is this going to be the initial or the final speed? Well, this is at a point that is downhill. So it sounds like that would be a v final. It doesn't mention a v initial. So the problem, I think, would have to give us that. but we're trying to find this V final relative to some V initial after we've gone through this displacement of 57 meters. Okay, so if we want to figure this out, we're going to focus mostly on the setup here. We need to know what force is doing work here, or how much force is doing work, because once we know the work, we can figure out the amount of speed using our work kinetic energy theorem, just like we saw in the last example. So rather than doing that all over again, we're just going to focus on how we can get that amount of work based on the amount of force. So here we're going to focus on solving instead for the amount of work, just to start, and know that ultimately that would connect us to the final speed. In order to do that, we're going to need to identify the forces acting on our skier, right? So what are some of the forces acting on our skier? Well, one is the gravitational force, mg. What direction does the gravitational force act? It acts straight down. So that one's going to be pulling down with a magnitude of mg. What other forces are on the skier? Well, the normal force, right? So the normal force, because of the slope, is perpendicular to that slope, so pointing out from the surface in the normal direction, perpendicular. Okay, any other forces? There's also this kinetic frictional force. What's the direction of that going to be? It's opposing the skier's motion, so that's going to be against the motion or up along the slope. So that is an F sub K. Now, which of these forces is contributing or detracting from the overall motion of the skier? Well, the frictional force is one, but it also says that the skier is accelerating because of the gravitational force despite this kinetic frictional force. So there's going to be some factor of the gravitational force that's enough to overcome the frictional force. But how much of it? Well, that is where we want to figure out how much of this gravitational force is acting along the slope. So we've done this a few times at this point, where we can break this down into a component of the gravitational force that is acting along the slope and another component that is just acting, pushing the skier into the slope. And you could show that this angle up here would be 25 degrees. Because if it was flat, then this green arrow would be pointing in the same direction as the blue arrow, but instead we're tilted or offset by 25 degrees. And so to get the component that is along the axis, we're going to need mg times sine of theta, or sine of 25. And this is the component that is opposing the frictional force that is moving the skier along. So if we want the net force contributing to the skier's motion, it's going to be mg sine of 25 less this frictional force. So that is the key details to this problem to set it up. Let's check out the full solution to solve for the work on the next slide. So we have our free body diagram here where all the forces are shown, including breaking down the gravitational force into a component into the slope and a component along the slope. So the net force doing work is mg sine of 25 minus the force of kinetic friction. If you calculate that with the numbers given in the problem, you should get 169 newtons. If we want to find the work, we can use that net force and plug it into our force in the work equation times cosine of 0 degrees times the overall displacement, 57 meters. So you get a work of 9,600 joules. If you want to find the final speed, then you would have to be told the initial speed, but you know the mass of the skier, so you could then use our work kinetic energy theorem that the work is equal to the final kinetic energy minus the initial. and you would be able to get there. So that highlights the different part of this problem, and I encourage you to work through the rest. You can make up some initial velocity like VO is equal to 2 meters per second. So then what would be VF be equal to? You can see. If you have questions, please ask away. I would love to help further. So I'd be happy to do so.